Now that we're able to add nodes to our list, both at the head, at the tail, or at any index, it's time to create functions that will delete nodes. And what I want to do for this video is I'd like to create a function that will delete the head node. So let me go ahead and create a function prototype. It's going to be a node data type, and we're just going to call it pop head. And again, we're going to mirror the language of the stack data type where you push data in and you pop data when you remove them. And for our parameter, we're going to have a node double pointer head. So we're going to use a call by address. So we're going to use the address of this head and insert it into this parameter as an argument later on when we call this function. So here on the right hand side is a pictorial representation of what I currently have here in our main function in terms of our linked list. And it's just 10, 20, 30, 40, and 50. Let me go ahead and compile that. And so the thing that we want to do for this function is we want to remove the very first node, which is 10. Let me go ahead and copy this function prototype and let's create a definition for it at the bottom. So before I start coding, let's go over the logic real quick. Let's take a look at the right hand side. So I'm going to go ahead and create an activation record for our pop head function. And so we know that we're going to have a head that will hold the address of this head down here in main and will be pointing to our very first node. The thing that I want to do is I want to create another pointer. I want to create a temporary pointer. I'm going to call it temp. The reason why I'm calling it temporary is for obvious reason. We are going to delete whatever node temp is pointing to. And so that's why we're going to call this node temporary. So in this case, head is going to be pointing to head. And so what we want to do is we want to delete head. But before we can delete head, we don't want to break this link. We have to move our head node to the second node. And then we want to delete this node right here. And then our indexes will automatically change and this will become a 0, 1, 2, and 3. Let's go ahead and create these pointers in our code on the left hand side. So the first thing I want to do is I'm going to create a node and I'm going to call it temp. And again, because we're using a double pointer here in our parameter, we want to make sure that we have a star for our head variable, because a double pointer holds the address of a single pointer. So now we have these two in the pictorial representation. As always, our very first condition is if our list is empty. So if we don't have anything in the list, that would just mean our head node is pointing to null. If that's the case, if head is pointing to null, what we simply want to do is print f and the list is empty. So after we print the list is empty, we just want to simply exit our function. So we're just going to say exit 0. And that's it for our condition. So let's go ahead and compile and run this. So I'm going to comment these out. Pop head. And in our parameter, we're just simply passing the address of head. The list is empty. Okay, so that works. So now our second condition is, what if we only have one node? I'm going to draw it here on the right hand side. Let's just say our head, and this is our temp, and they're both pointing to our only node. In the case where we only have one node, what we want to do is, all we want to say is, if this temp's next is null, then we just want to free temp, and then we want to set them both to equal null. Let's go ahead and do that. Else if temp next link is pointing to null, then all we want to do is we want to free temp and assign both head, so that way it's not a dangling pointer, to null, and we also want to assign temp to null. Let's test this condition. Before I do that, let me comment this out. And as you see, we should only have one node, and that is a 40. And then after we run this function, it should delete that 40. And the list is empty. On our final condition, if the list has more than one node, let's take a look at this. Head and temp are pointing here. All we want to do is we want to move head to here, to our next node, and then delete this first node, and then set temp equal to null. Let's go ahead and code that. We want to move head, and how do we move head? By simply moving it to temp's next. Let me create a print statement that will allow us to know what's been deleted. So let's just say node was deleted. Let me create a counter so that we can address this format specifier for our index. And really, it would just be a 0 every single time, but just for best practice, let's go ahead and just create one. Let's put it right here, NI 0. So now let's go back down. Here we're going to have I, and then here we're going to have temp, arrow, data, and let me put this in 2 lines. Okay, so this should print out what's been deleted, and then after that we just want a free temp, and then we want to set temp to equal no, or set it to no, because we don't want a dangling pointer. Let's go ahead and test this condition. So here I've uncommented all of the functions. They should all be working now. So it should pop 10. Let's run it. Index 0. Let me move this down because you see how node 0, it's kind of, let me fix the formatting for the print statement. So let me put a period here, and let me do 2 new lines. New line, new line. Now let's run it. Okay, that looks a lot better. So node index 0 with data 10 was deleted, and this is our current list. 20 now becomes index 0, 30 becomes index 1, 40 becomes index 2, and 50 becomes index 3. And our number of nodes that we're holding is 4. So 1, 2, 3, 4. So now let's test all the conditions. I want to add this print statement to all of them so that way we know what's been deleted. So let me just copy this. Let's put it here. This is if we have 1 node. We don't have any nodes. Okay, so let's test it. Let me comment this. So this should give us the list is empty. Perfect. Let me uncomment 1. The list is empty. But if you look at our print statement, node index 0 holding the data 40 was deleted. If we have 2 nodes, 30 was deleted. And again, our final test run, there it is. So this pophead function is a call by address. And so when we call it here in our main function, we call it by address. But we can also write this function as a return the address in the same way that we've written all of our functions that have a 1 at the end of it. So let's do that. It's not a hard fix. It's just another way that you can write this function. So let me copy this, but instead of a double pointer, we're going to do a single pointer, and then we want to make the name of our function a pointer because a pointer holds an address. So this will hold an address, and when we return the address, when we return this, we'll just set it just like this because it should return the address to head. Now let me copy this function and make some changes, and I'll put it just right above it. Let's fix this. So we want to make this a pointer, and then we want to make this a single pointer. And so now anywhere that you see head, just remove the star. And then at the end, the only thing you want to do is add the return head. So we're going to return this address. And let me run it. But this time, we'll call it pophead. Oh, forgot to put the 1 on it. So let's call it pophead1. And then we want to remove this address because now we're returning. So we simply just want to pass in head because head is already an address. Let's test all the conditions. Let me comment out these functions. First condition is if our list is empty, the list is empty. The second condition is if we only have 1 node, there it is, and it makes our list empty. Our final condition is if we have a full list, and there it is. So 2 ways you can write the pophead function as with our other functions. You can write it as a call by address, or you can write it as return by address. That in a nutshell is the pophead function. And in terms of time complexity, since we're just popping the first node, it's just 1. And so it's really efficient. On that note, thank you for watching.